Hi, my name is Kory and I'm a senior electrical engineering technology major here at Alfred State College. And for my senior project, I would like to create an electric longboard. Now my background is that I've been skateboarding and longboarding for over 10 years competitively, as well as electric longboarding for over 1 year now. I've also taken several courses here at Alfred State College on AC and DC motor design and their application in real-world technologies, and I've seen how effective they are. Now, what is an electric longboard? Well, to start, you must know what a regular longboard is. A longboard is an enlarged skateboard, usually 9.5 to 10.5 inches in width and 34 to 42 inches in length. They are designed for high speeds and to go long distances without worry. Now, an electric longboard is simply that, except powered by hub motors in a 1, 2, or 4 motor configuration, and they are powered by lithium-ion batteries. A normal store-bought electric longboard can go an average range of 9 to 12 miles and travel roughly 16 to 25 miles per hour. And they are driven by a wireless Bluetooth remote that you hold in one hand while you ride. For this project, I've taken a design from one of my favorite YouTubers, whose name is Jehu Garcia, as he specializes in RC and electric vehicles. Now, one of the things that makes his design unique is the 3-phase motors that are from a hoverboard. A hoverboard was a consumer item that came out several years ago, which was basically a self-balancing unicycle. Now, as most trends do, they come and go, and so the market really built up and then crashed, so plenty of these motors are laying around on eBay for very cheap. And for this project, I'll be having my lithium-ion batteries running through an XT60 connector, which will control the whole board with a wireless remote. The power that goes through the connector will go to the shunt, which will then be displayed on the battery meter on the top part of the board to show us how much power we have left and how long we have until we run out. Now, also from the shunt, we will have our speed controllers, which are basically our motor driver circuits. And since we are working with a 4-motor design, we'll have to have 2 separate motor driver circuits working together in sync. For this, I have done a cost analysis on all the parts that Jehu Garcia has listed, and I have found it to be roughly $598.74, with a couple variables in there, such as shipping and tax, which may or may not change due to this being around the holiday season. To save on this budget and to keep it a little bit below $598, one of the things I could save on would be the board cost. As I have many boards at home, it just depends on if this one fits my criteria and the weight and the specs that I require to fit all of the motors and all the components underneath. As well as I have several sets of trucks at home, which trucks are the part that the wheels will be mounted on to hold them stable and allow us to turn. Now, as I said before, we will be using these hoverboard motors, which they're 6.5 inches in diameter, which allows them for very easy on-road to off-road capabilities. These wheels are also very unique because they have a forward and reverse that works in the exact same power configuration due to the unicycles being self-balancing. These also have regenerative braking, so when the motors are not in power, power will flow from the motors themselves back to the battery packs and help to charge the battery and to keep our power supply working for longer. And these motors also come in a stock Y configuration. Now, one of the upgrades I'm considering doing for this project is taking the stock Y configuration and converting it over to Delta. Now, as I have listed, motors in Delta often have less torque at the start, and you can achieve a 1.7 times higher top speed. Now, that may not seem a lot, but when it comes down to miles per hour, it may turn into a 1 to 2 mile an hour advantage over a Y configuration. Now, some benefits about being in Y would be that I would have more torque available at the start, which means I'd have an easier starting time, as well as that they run cooler. However, since this board is going to be open, the air will be hitting it anyways, and it'll be self-cooling. For this project, I'll be using 18650 lithium-ion batteries, which are a very common battery. They're often found in electronic cigarettes as well as laptop batteries. They're normally 3.7 volts in capacity, and as well as 22 milliamp hours. For this project, I'll be requiring 40 batteries in total. However, I have found a deal for 99 used laptop batteries for only $50, with a 60% yield of them being up to the charge that is listed. Now for this project, I'll be using 10 packs of batteries with 4 batteries per pack in parallel, and these packs will be wired in series, as shown here. So we will be having all of our packs in 2 separate columns connected by these little tiny copper plates. That way we have a nice power flow without having too much resistance. And since we have these wired in parallel, we're basically creating large single-celled power supplies that are going to be wired in series to create one large power bank that we can rely on to power all of our motors. Now for this project, there are some unknowns, but I would like to get through my ideal values first. For this, I would like to create a board that is able to go 10 plus miles, which 10 is on the lower side of already store-bought products. However, since I'm using hoverboard motors instead of regular precision-made hub motors, they are often lower in power, as well as they are higher in power consumption due to their larger size. I'd like to have a minimum of 10 miles an hour, which is below the standard store-bought products. However, the hoverboard motors do have a low top-end speed because they're only made to go around small areas such as a house or simply down the sidewalk. And I'd like to use a 36-inch board, which is my comfort zone on my normal longboards. However, I might be able to go up to a 42-inch board in length. That way I can have more power packs underneath, as well as more room to mount the components that I'll require. I'd also like this to be underneath 30 pounds. That way I have a lighter rider weight, which I do not know how it affects my weight and speed as listed in my unknowns. I'd also like an easy rechargeability, as well as this thing to cost under $650. I gave myself a large margin just in case things went wrong. Now for my unknowns, one of the biggest problems I'm running into is I don't know how to build a charger yet. However, I've found several online forums and schematics that will allow me to build such things. I also, as I said before, don't know how the weight of myself compared to a lighter rider will affect the board. I also don't know how it will affect the regenerative braking and the amount of power that is created running back to the power supply. And I do not know how long it will take to charge all of these cells, as I have not designed a charger yet. Why is this project important? Well, after my 4 years here at Alfred State College, one of the things I found the most interesting was AC and DC motor design and their various applications in real-world technologies. After college, I plan on getting a job in which I use these AC and DC motors, such as public transit or aviation. And for me, my one true love of longboarding, mixed with what I learned at school, could be a great way to expand my knowledge and actually find true enjoyment in hobby electronics. Now here are all the works cited that I have, and all of the references to them are linked in the description. I hope that this product has lived up to the standards and qualifications that we require here at Alfred State College. Thank you.